Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear. And this is my new feature I've been running for a couple weeks on the Math Lovers book. This is a 3-volume series I wrote from 2019 to 2022. You guys can buy any one of these books or any combination of them on Amazon.com. They're available both paperback and Kindle. I think it's $30 paperback, $9 Kindle. You might want to check them out. I think they're a good read, and the first two are textbooks. The first one is more recreational math, kind of high school, advanced high school level recreational math. Second one is a more academic. I talk about things like calculus and probability and statistics, and it's a little more advanced. I'd say maybe first or second year undergraduate level. And then the third volume is problems and solutions. That has problems pertaining to each chapter in the first two books, as well as solutions, the odd number problems. I don't give solutions, the even number problems, because I like you to figure some of them out for yourself. In real life, there are no solutions given. So anyway, that's just a little bit of an overview of the Math Lovers book. And this new feature I'm running, I'm actually doing free lessons on the Math Lovers book, and I'm up to chapter two. I'm about halfway through chapter two. I'm talking about prime numbers, section 2.2. So chapter two is on natural numbers. Primes are very important class of natural numbers, as I'm sure you all know. And today I'm going to talk about formulas for generating prime numbers. So let's begin. So just a little overview here. For a long time, since primes are so important and so interesting, for a long time, mathematicians were wondering if there were any formulas for generating. I mean, I already talked about the sieve of veritasities. That's still the fastest known method we have for generating all the primes up to some bound. And it's a little bit cumbersome. I mean, it is efficient, but, it'd be nice if there was a formula, some function. We could just plug in some value of n, and f of n is always a prime. And, maybe we'll generate all the primes, maybe some of them. I mean, I guess the ideal formula would be one that would generate every prime for some value of the input. And then, if we can't do that, maybe just some of them. And and nobody's found such a formula. I mean, that's not quite true. There are formulas for generating primes, but they're very complicated formulas. And it turns out that all the formulas we know so far are at least as complicated as the sieve of veritasities. As a matter of fact, some of them really are the sieve of veritasities in disguise. They're kind of if you kind of decode them, it turns out they're just kind of a funny way of expressing the algorithm required to generate all the primes. They're pretty clever functions. I think somebody discovered a function of 26 variables. Um, you know, uh, and I think every time you put a positive integer for any one of those values, they always get a prime. But they're not. It's not a useful formula because it's too complicated to use. But there are some simple formulas that are pretty close. They don't always generate primes, but I'm going to talk about a couple of them. So first, the first effort to do so, I think, was by this very famous French mathematician named Pierre de Fermat. And he came up with what are called Fermat primes today. So what Pierre de Fermat, he lived in the 17th century in France, and he was a very famous number theorist, and he came up with a formula, a very simple formula. He said f sub n for the nth Fermat number. He thought these numbers were all prime, but he said if you plug in any value of n, any non-negative integer value of n, 2 to the 2 to the n plus 1, he conjectured, was always prime. And that's what's called a power tower. This thing 2 to the 2 to the n grows very fast. I mean, but what's kind of interesting about his formula, it works for the first five. And you'll see that these grow pretty fast. I mean, so let's just look at the first five of these Fermat numbers. F0, that's 2 to the 0 plus 1. Well, 2 to the 0 is just 1. So that would be 2 to the first plus 1. 2 to the first is 2. So 2 plus 1 is 3. And indeed, 3 is a prime. Pretty easy to see. What happens when we plug in 1? Well, then we get 2 to the 1 plus 1. 2 to the 1 is 2. So now we have 2 squared plus 1. 2 squared is 4, so 4 plus 1 is 5. Again, 5 is prime. So far, so good. Let's keep going. F2. That's 2 to the 2 to the 2 plus 1, or 2 to the 2 squared plus 1. 2 squared is 4, so that's going to be 2 to the 4th plus 1. 2 to the 4th is 16, so 16 plus 1 is 17. Again, 17 is prime. So it looks like this is true so far, but you can actually do a couple more. Those turn out to be prime as well. F3, 2 to the 2 to the 3 plus 1, that's 2 to the 8 plus 1. 2 to the 8 is 256, plus 1 is 257. That's prime too. And the biggest of these, F4, 2 to the 2 to the 4 plus 1. I think this is the biggest one that Fermat was able to check because he lived in the 17th century. It was hard to factor large numbers, but this was the biggest one he calculated. 2 to the 16 plus 1. 2 to the 16 is 65,536. You add 1, you get 65,537. And that's also prime. And since all 5 of these numbers are prime, including the last one, which is a pretty big number, and numbers of that size are kind of rare, if they're prime. I think the probability that a number this large is prime is about 10%. So the fact that it's prime led him to believe, and all these other ones are as well, kind of led him to believe that they all were. Kind of a natural assumption. I guess he couldn't go any higher than this. But unfortunately, I think it was shortly thereafter discovered that the next one fails. F5, I think it was discovered maybe in the 18th century. I don't know who discovered this. This was composite. Um, but it turns out F5, that's 2 to the 5 plus 1, which is 2 to the 32 plus 1. That turns out to be composite. You can write it as the product of two primes, and they're pretty large primes. 641 times 66,700,417. So this number is not prime. It's composite. And you might think, well, one fluke, maybe the rest are prime, or maybe most of the rest are prime. Actually, it turns out, I think that all these Fermat numbers have been computed up to F32. Maybe not computed, but they've been determined. It turns out that every other Fermat number that everybody's ever tested up to F32, I think they've all been tested with the subscript going up to 32. So F5 up to F32, that's 28 Fermat numbers. All of those are composite. And now, most mathematicians think, and there's good statistical arguments for this, now almost every mathematician who studies these believes, even though it hasn't been proven yet, but most of them believe that every Fermat number past F4, F5, and so on, Fn when n is greater or equal to 5, it's now conjectured that all those numbers are composite. So there's only 5 Fermat primes. He thought there were infinitely many, but there are only 5 as far as we know, and they're only the first 5. I want to say one more thing about Fermat primes, but I didn't talk about this in my book, but I think this is a really fascinating aspect of Fermat primes. You might wonder, well, who cares about these things, right? I mean, we found 5 numbers of a particular form that all happen to be prime. Well, what good are they? It turns out, this is what Gauss discovered when he was a teenager, I think. I don't know if he discovered the whole thing, but it turns out that for every Fermat prime, it turns out that a regular polygon with that many sides is constructible. And those are the only prime numbers for which a regular polygon with a prime number of sides is constructible. Pretty wild. So you can construct a regular polygon with 3 sides. That's just an equilateral triangle. And I'm talking about construction with compass and straightedge. This is kind of a classical, geometric constructions you probably learned when you were in high school, when you were learning about, geometry. They're kind of cool. I think they're fun. But it turns out, that not very many regular polygons are constructible. With compass and straightedge, and those with a prime number of sides, there's only 5 of them that are constructible, and they all have Fermat prime number size. So, for instance, a regular pentagon is constructible. I think the Greeks even knew how to do that. But then a regular 17-gon or heptadecagon, if you like, that turns out to be constructible too. And Gauss, Carl Friedrich Gauss, I think in 1796, when he was 19 years old, he was the first person to construct a regular heptadecagon, regular 17gon with compass and straight edge. It's a very complicated construction. I don't even remember it myself. I'd have to look it up. It involves about 20 steps, but if you follow the steps, you can construct a regular heptagon. And you can't construct like a regular 7-gon or 11-gon or 13-gon. You might think you could, but you can't. The next one you construct with a prime number size is 257. And the remarkable thing, Gauss did the first of these. I mean, not the first, the second, the 17-gon. But since there have been other mathematicians who constructed all the rest. And I think there was a whole book that was written on how to construct a 65,537 gon. I don't even know who did this, but whoever did it, I feel sorry for him. He probably spent several years just working out this construction of this regular 65,537 gon. He must have been kind of a masochist to do that. But he did construct it. I've never read the book or seen the book, but it has been done. So all these regular polygons have been constructed. Believe it or not. Anyway, I just thought I'd mention that. And then, can we do better? Well, it turns out we can do a lot better. It turns out that there are certain quadratic sequences. These are just quadratic polynomials, polynomials that form ax squared plus bx plus c. Probably learned those when you're in high school. So it turns out that there are some quadratic sequences of integers which yield like a lot of primes. Not always primes, but pretty close. And here's three formulas. So n squared plus n plus 17. It turns out that for any value of n from 0 to 15, I believe, that's 16 values of n, this always yields a prime. Well, that's pretty wild. I mean, you can try it yourself. You can do even better. 2n squared plus 29 when n goes from 0 to 28. I believe this is always prime. That's 29 primes. And the best one we know, I mean, it's not the best we know, but the best we've known for a really, really long time was this formula discovered by Euler, the third one. N squared plus n plus 41. This yields 40 consecutive primes, starting with 41. And when n is from 0 to 39, that's 40 values of n. This always yields a prime. It starts out, you can check yourself, 41, 43, 47, 53, 61, 71, 83. They're all prime, which is pretty wild because I mean, this isn't a coincidence. I mean, the odds of each of those numbers being prime is kind of low, especially as the numbers get big. They go all the way up to 1601. But then the next one, the 41st number, fails, 1681. That's 41 squared. It's pretty easy to see that has to fail. And then the funny thing about this, I don't mention this in this book, but if you keep going with Euler's sequence, n squared plus n plus 41, it turns out that you get a lot of primes. I mean, they're not all prime anymore after 41, but you get a very high density of primes. If you let n go all the way to 100, I think you get like a total of 86 out of 100 primes. Only 14 more numbers in the sequence are composite from 41 to 100. 14 out of 60. So you're still getting like 3/4 of the numbers from 41 to 100 prime. And the biggest of these is almost 10,000. I think it's 9,941, if I'm not mistaken. And that one is also prime. So, pretty wild that this formula just happens to generate a lot of primes, a high density prime. It turns out there's a reason for this, but it's a very, very complicated reason. It involves algebraic number theory. It involves something called the modular J function. It's a very complicated proof. It's the same reason why there's a number called the Ramanujan constant, e to the pi times the square root of 163. It's an irrational number, but it's very, very close to an integer. Like it's only about 1 part in a trillion away from an exact integer, which is pretty wild. I think Martin Gardner in 1975 even posted an April Fool's joke claiming that it was an exact integer. And at that time, it was within about the limits of computation to be able to determine whether or not it was an integer. So he actually did fool a lot of people. It was an April Fool's joke, but I think for a week or two there were a lot of mathematicians that thought this number really was an exact integer. It turns out it's a transcendental number. But I'm digressing here. I guess I just want to say one more thing. So this Euler sequence, n squared plus n plus 41. Here's the numbers written now. I probably should have showed you this before. And it fails when n equals 40. You get 1681. And all these other numbers on this list are prime, like I said. But there's another construction. This came later. This is due to a Hungarian. I think he was Hungarian. He was from Eastern Europe anyway. His name was Stanislaw Ulam, and he was a pretty famous mathematician in the 20th century. And then one day he was bored. I think this was in the 1950s. He was at a lecture. He got bored, and so he started doodling. He decided just for the hell of it he was going to draw a square spiral that looks kind of like this. And then he was going to plot where the primes lie on the spiral. And it turned out, he didn't expect this at all, but it turns out that the primes seem to be, congregated along these diagonal lines. And nobody expected this. And this is actually the same phenomena about this Euler sequence. The Euler sequence is actually one of these diagonal lines. I'm not sure which one. But it's the same reason. I mean, we can kind of translate this into algebra. The fact that these primes lie on diagonal lines is kind of the same idea that we have dense quadratic sequences of primes. So I think he kind of discovered that fact just by doodling. It just kind of shows you sometimes when you're bored, you can still come up with some pretty amazing discoveries. Another example I know of this, there was a physicist named Don Glaser. I think my aunt even dated him. They didn't get married, unfortunately. He ended up winning the Nobel Prize. She could have married a Nobel Prize winning physicist instead. She married the head of the RTA in Cleveland. She didn't do too bad though because he became a millionaire from what he did with the RTA. But I mean, but the thing I wanted to say about Don Glaser was that one day he went to the University of Michigan, which was the same school I went to, by the way. And I guess he liked to drink like most students do. So he's in the bar one night. He got some beer. And I don't know why. I guess he was bored. Maybe he wasn't picking up any chicks or something. But he was just kind of mindlessly, staring at the bubbles in his beer. And then while he was daydreaming about that, he came up with the principle behind the bubble chamber. He figured out how bubbles form in liquid, and then he invented the bubble chamber based on the dynamics of the bubbles in the beer he was staring at. So, you never know where inspiration will come from. Of course, you have to have all the background to begin with so you know what you're thinking about. But I know a few other examples like that as well. Anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time.